All right, this section of videos is probably not going to flow very seamlessly with the other videos that I'm going to put together in the playlist, but I want to definitely talk about the normal distribution and finding probabilities for the standard normal, which I can't seem to find in my list of video selections, and that I want to attach with this chapter on the continuous distribution, the normal distribution. So first of all, let's review our ideas from Chapter 1 of Triola's book about continuous versus discrete. So in Chapter 5 of Triola's Essentials of Statistics, Edition 5, we found discrete probability distributions, and here in Chapter 6 we're going to talk about continuous. So remember that continuous, what we're talking about is something like on a number line. So on a number line we have 0 and 1 and 2, or -1 and -2, and those are our discrete points. That's what we talked about in Chapter 5. And then what we're talking about in Chapter 6 is the continuous, and that's everything that's possible here on the number line. So discrete being countable and continuous being the difference between just measurable points and then the countable points, and then between the measurable, so like a wire here as the number line. And how could we measure the wire? Well, we could go down to smaller and smaller and smaller increments, and that's the idea of continuous. So we are going to talk about the normal distribution in this chapter, and there are many real-life applications and real-life data sets that conform to this type of distribution. And in the middle of the chapter, approximately, we'll be talking about the central limit theorem, which makes many more applications to the normal distribution. So this lovely piece of function here, this is the normal distribution. And what you have to understand about a distribution is it is just like any of the curves or any of the functions that you would have found in an algebra class. It's just that these give us curves, and these curves are then associated with probabilities, which are areas under the curve. So this is for any normal distribution, and the normal distribution has two parameters. The parameters that we discuss are the mean and the standard deviation. So the normal distribution is dependent upon E, the natural base raised to the -1/2 power, times x minus mu divided by sigma, all quantity squared, and completely over sigma divided by the square, or times the square root of 2 pi. So this distribution is a symmetric bell-shaped curve, and the symmetry is about the vertical line x is equal to mu. In other words, it's symmetric at the mean, and the x-axis forms a horizontal asymptote. The inflection points occur at the 1 standard deviation, and the area under the curve is equal to 1, and there's no area under the curve for any particular one value. So let me just draw you a little picture of all of that summary of information. So here's our normal curve, and this normal curve, we have the x-axis here down at the bottom, and the normal curve comes in, approaches, but never touches, never crosses the x-axis. The idea is of asymptotic behavior. Here at the exact middle, that's where we find the mu, and here at the inflection point, that's where our curve goes from being concave up to concave down. That's the 1 standard deviation mark, and the same thing on this side. Those points too are symmetric, so we have negative sigma over here and positive sigma over here. And this area, everything that I could shade underneath this curve, this would all add up to 1. Now the idea is that the area under the curve adding up to 1, we can't really ever find all of that, right? Because it keeps going and going and going and going. In other words, there's always infinitesimal amounts of probability no matter what random variable you're talking about for a normal distribution. Now the other thing that we want to discuss is something that's related to geometry. And if you remember from your study of geometry, the area of a line, or a line has no width. So there is no area under any particular point on a curve, because that forms a line, and a line has no width, and therefore we would have no area. So it doesn't make any difference in the normal distribution if x is greater than some variable, or if x is greater than or equal to some variable. These two things are equivalent to one another in a normal distribution. Now, if you remember right, in a discrete distribution, those two were very different from one another. So that's what we're talking about in this particular instance. So now moving on, we're going to take a look at how we can, this is something that I can't do on the computer because I don't have an emulator for the TI, but these basically show how these curves will change as we have different values of means and standard deviations. So what you'll notice if you do this little exercise with your TI calculator is that as you change the mean, if here's our normal line, right? If we change the mean, we'll go from having a curve here, maybe, to having a curve here, maybe, to having a curve here, maybe. But they're all the same height and they have all the same width across here. Now, as you change the standard deviations, as we have smaller standard deviations, we'll see our bumps go higher, and then the smaller we get, the fatter, wider, basically, these things get. So that's what you'll see when you do these little exercises in my notes there. Now moving on, so the chapter 6.2, the standard normal distribution. This is really where I need our work to begin. So the standard normal distribution is a continuous probability distribution, and it's based upon this distribution that we just saw, the normal distribution, but where our mean is equal to a 0 and our standard deviation is equal to a 1. When this is the case, we are going to have a standard normal distribution. And a standard normal distribution, we are going to always label this as a z. And if you remember, we've had z-scores before, and that's exactly what a z-score is. It's a standardized score, and it's standardized with respect to the mean and the standard deviation, and it brings back to basically a mean equal to 0 and a standard deviation of 1. It standardizes those. It's a transformation, in other words. So this part right here, I'm not going to go over this. This is about a continuous uniform distribution, and this is just going to help us to talk about how we can see on a density curve, which is what this is for the normal, how we can see areas. So we hopefully we talked about that in terms of our binomials enough that we understand that. But maybe we didn't. Maybe I should go over that.